Hello, everybody. My name is Nguyen, and today I'm going to present my PhD thesis. My supervisory team consists of Associate Professor Minh Chen and Dr. Ritash Chandra. Before I move on to my PhD thesis, I'd like to give a quick intro into Bayesian inference algorithms. They are used a lot in increasingly complex machine learning models, and they provide a natural and principal tool for statistical inference to compute and sample from the posterior distribution. And since the posterior probability distribution are often highly dimensional and highly non-convex, the challenge of computing and sampling from it can addressed by MCMC and variational inference. For my research thesis, I'm addressing some limitations to both sampling methods. For the first project, since MCMC has been limited in the scale of model exploration, reversible jump MCMC allows sampling of parameters of variable lengths. In my project, I implement reversible jump MCMC on Bayesian neural networks that feature dynamic input and hidden neurons. And we showed that our framework allows a more dynamic exploration of models with a wide-ranging architectures while featuring uncertainty quantification for the overall prediction and also network topology. Given the time constraint of my presentation, I will focus on my second project. While MCMC offers sampling from the exact posterior distribution, variational inference scales better for complex models with large number of parameters. This cycle represents 4 different variations of variational Bayesian that I will add into to make the original method more efficient and accurate. Before going into one of the variations, I'd like to give a quick intro into variational Bayesian, which is a family of techniques that approximate the intractable and costly posterior distribution by providing an analytical solution Q that belongs to some tractable family of distribution. The locally optimized approximation is obtained by minimizing the KL divergence and maximizing the lower bound. And since we are talking about minimization and optimization, VB becomes an optimization problem that is suited for explorations of data sets that have high dimensional posterior distribution. While likelihood is intractable, approximate Bayesian methods are useful to conduct Bayesian inference. Most popular likelihood Bayesian methods are approximate Bayesian computation, ABC, and Bayesian synthetic likelihood, BSL. My research actually focuses on the latter, in which it is useful for likelihood-free inference when the summary statistics follows an approximate Gaussian distribution. BSL is very useful because it reduces the curse of dimensionality, often associated with ABC methods. It is also very convenient because the parameters of the algorithm can be tuned easily. In order to give you a better idea of VBSL, I will run you through the process of the method. So we are given observed data that follows some unknown true distribution and are generated from some complex models. Under the assumption that there exists a class of thetas for our models that correspond with the unknown true distribution, we want to produce draws of theta from the exact posterior density. However, in case of models that are very complex, the model likelihood is intractable. Hence, we need to simulate the likelihood by simulating m data sets from our model given our thetas. And we then reduce the new data set into summary statistics because we want to significantly lower the dimensions of our the data sets that we're working with. So now we have a new likelihood, which also is still intractable. So we need to estimate this with a multivariate Gaussian distribution. So the big question is that since mu and sigma are unknown, how can we obtain this and get the likelihood for our multivariate Gaussian distribution? In fact, we will obtain the mu and the sigma by taking the mean and the covariance of those m data sets and feed them into our multivariate Gaussian distribution and calculate its density. If you look at the process of VBSL, you can see that the efficiency of BSL relies on the normality assumption of the summary statistics. So we propose using Wasserstein gradient flow to transform the distributions of the summary statistics into a Gaussian distribution. To illustrate how it works, I will use a very simple data generating process. So we create these random errors that are heavily skewed, and this model will be able to help us generate the data, but will not have a closed form density. If you can see, we first just generate some observations at theta equal to 0, and we'll find that the summary statistics, which in this case are just simple mean and variance of the whole of all the data set of all the observation. And you can see that this summary statistic did not follow a multivariate normal distribution. However, once we apply our Wasserstein Gaussianization transformation, you can see that the summary statistic now follow a multivariate normal distribution. And in fact, now that we incorporate Wasserstein Gaussianization into VBSL with the same toy example, you can see that the MSE between the true theta and the posterior mean estimate is the lowest for the VB with Wasserstein Gaussianization, actually significantly lower than the original conventional methodology. I will present a quick example just to show how we use VBSL. So in this case, we are talking about the example of a Fowler's toads at Long Point in Ontario, Canada. There are 3 parameters of the model to look at the toad's movement. The first one is the net displacement that follows a symmetric zero center stable distribution. The second one is 3 versions of our model, which signifies the returns of the toads. This is under the assumption that the toads will travel during the day, and at night it will decide whether it should return to one of the refuge sites or to some refuge sites or not. So there are 3 possibilities of return. The first is random, just choose any refuge site. The second one is the nearest return, and the last one is a distance-based return, which in this case is the distance, the probability of returning to a given site decays exponentially with the distance to that refuge site. And so our model now has 3 parameters, the overnight displacement, the probability of return, and the distance to the refuge. And as you can see, this model is extremely complex. And I'm saying that because in animal movement, or honestly in any field, there is not only the movement rules, the biological constraints, but also the cognitive map of the animal itself. So therefore, the complex models are needed. However, the outcomes will not be expressible in terms of analytical likelihood functions. But with VBSL, we can generate the closest estimates for the parameters of the true model, no matter if they are extremely complex or don't have closed form density. And from the new estimated parameters, we can make inference on larger outcomes. And all of them are just through the use of only slice observations. Throughout the project, I have encountered some challenges, such as finding ways to prove that the addition to this conventional method helps, the math behind this method is sound, and most importantly, the code that I use is executed optimally. I have to use JAX, run GPUs, use AWS in order to improve automatic differentiation and just-in-time compilation. As I have mentioned, VBSL is suitable for large-scale applications. In fact, ABC methods is the simulation-based inference method is actually originally developed for the field of population genetics, because the number of possible genetic histories and immediate states leading to a given outcome make explicit likelihood calculations intractable. Another example is in the production of clean steels. Whenever you produce steels, the occurrence of imperfections are unavoidable. However, what can we do if we only have a slice observation of imperfections on a planar slices of the steel, while we want to see the imperfections across all parts of the steel when we do manufacturing? So BSL can help us make inference, even just a slight observation. So advances in computing, artificial intelligence, and machine learning capabilities are causing a proliferation of black box models in any aspect of our life, from large-scale problems like genetics to everyday behaviors of everybody. And so, although the absence of likelihood function for these complex black boxes have always prevented some formal statistical analysis. The advances in using inferences from simulation-based models have made everything possible now. I believe that washer-style Gaussianization will significantly improve the conventional VBSL methodology, as BSL has always relied on normality assumption, an assumption that has never really been challenged by previous literature. I hope that through my research, I can help people understand and analyze precisely how black box models can produce the conclusions. Thank you so much for your attention. And I'm open to, if you have any questions, please feel free to send me an email. Thank you.